Hello students, hope in the previous two classes we saw what are the deadlock strategies and what are the ways the deadlock can be handled in the operating system with the continuity of deadlock concepts. Now we are going to see resource allocation graph. A resource allocation graph, as we saw introduction about resource allocation graph, let me recall what is resource allocation graph and how it will be helpful for avoiding a deadlock. Okay, so resource allocation graph is a pictorial representation of a complete system. The system may be safe state or unsafe state. One can easily deduct uh, the deadlock is present in the system or not by seeing the pictorial representation. So the complete system can be represented with the help of resource allocation graph. So what are the other information that it provides by the RAG? Okay, so there are some list of information that is provided by resource allocation graph. They are how many processes exist in the system. Okay, when the system execute some process, that we can easily get to know by seeing the resource allocation graph pictorial representation. So how many processes exist in the system, how many instances of each resource type exist. As we all know, in order to execute a process we need we need many resources like memory, CPU, and then input device, output device. So all the resources are required. So you can easily understand by seeing RAG how many instances of each resource type exist, how many instances of each resource types are allocated, how many instances of each resource types are still available, and how many instances of each resource type are held by each process. So how many instances of each resource type does each process needs for execution. So these are all the various types of information one can get with the help of resource allocation graph. Okay, so what are the two major components of resource allocation graph? They are vertices and edges. Vertices are further classified into process vertices, resource vertices, and resource vertices further categorized into single instance, multiple instance. So what is meant by process vertices and resource vertices? Process vertices represents the process. Okay, what are the process that CPU executes? That is what we call as process. Process is nothing but currently it's in execution. Some task is in execution. Some action is executed by the CPU, and they are represented with the help of circle. And with that circle, inside the circle, the name of the process is mentioned. Resource vertices. Okay, resource vertices represents the resources. As I said, input device, output device, CPU, memory, all these are all the types of resources. So that resources can be used by processes. Okay, how resources can be represented in the RAG? So it is represented with the help of rectangle, and inside there is a dot. That dot we that rectangle may have single dot or multiple dot. So it means that the resource of single instance or multiple instance. Say for example we have multiple tape drives are there, so of same type. Okay, multiple tape drive of same type, so that is what called as multiple instances, number of instances of same type. Okay, we have input device. What are the various types of input device? We have scanner, we have a keyboard, mouse. So all these are all instance of input device, so all are common. Okay, so these are all instance of resource type that the resource existing in the system. Okay, so depends upon the number of instances that exist in the system. Resource vertices may be single instance or multiple instance. So based upon the process requirement, the process may use single instance or multiple instances. Okay, and edges. The second component of a resource allocation graph is edges. So the edges that connects the resource and process. Okay, and there are two types of edges: the assign edge and request edge. So what is assign edge? So assign, in the name itself, you can understand assigning resources to a process. Assign edge represents the assignment of resources to the processes. So whatever resources that is required by the process, that resources can be assigned to the processes. So which is represented with the help of an arrow mark, where the head of the arrow points to the process, because the resources assigned to the process. So the head of the arrow points to the process and tail of the process points to the instance of the resources. Okay, request edges is nothing but requesting for resources, a process requesting for an resources. So resource edge represents the waiting state of a process for the resources, and it is represented with the help of arrow, where the head of the arrow points towards the resource and tail of the process points to the process. So if a process requires n instance of a resource type, then n assigned edges will be drawn. Okay, so here you can see resource allocation graph, how the resources are allocated to the processes. Okay, we can see as I stated in the starting of the resource allocation graph, it provides many information, right? Let us see with an example how what are the information which is given by the resource allocation graph. So this is a sample simple diagram that represents resource allocation graph. It gives various information. So with that diagram, what are the information you can give? The number of process, how many process are in the resource allocation graph in the system. Okay, P1, P2, P3, there are three process are in execution, P1, P2, P3. Namely, there exist two resources in the system. What are the two resources? R1 and R2. The resources are nothing but it is a need of process for execution. Say for example, a process one may need of memory for storing a data. Okay, memory is also one type of resources. Okay, so that is used by process P1. So resource R1 and R2. As you can see, R1 has only one instance, R2 has two instance of same type. Okay, and now what are the resources that is held by process and what are the process requesting for the resources. Okay, and see here, this is what we called as assignment edge. Resource R1 is assigned to process P1, assignment edge, and rectangular is represented for resource, circle is represented for process. Okay, and then requesting edge, we have one more edge, right? Request edge, process P1 requesting for one of the instance of R2. Okay, now here R2 resource R2, there are two instances. One instance is assigned to process P2, but the process P2 requesting for resource R1 instance, and one of the instance of R2 is assigned to P3. So these are all the with the simple representation we can get many information. Okay, that is the purpose why we want a resource allocation graph. Okay, now deadlock deduction. Okay, we saw many strategies to avoid a deadlock. Now deadlock deduction. Why they have introduced resource allocation graph concept? Because this can be used for deducting the deadlock and whether the system is in deadlock state or not. So the main purpose of resource allocation graph, it can be easily deduct whether the system is in deadlock state or not. So with the simple diagram, one can easily identify or determine whether the system can occur deadlock state or it is in a safe state. Okay, let's see the first rule in the resource allocation graph, where all the resources are single instance. Okay, in resource allocation graph where all the resources are single instance, if a cycle is being formed, then the system is in deadlock state. Say for example, here we have two resources, right? The first rule is when the resource have only one instant and it forms a cycle, then there will be a deadlock. The system will be in deadlock state. If no cycle is being formed, then the system is not in a deadlock state. Okay, this is rule 1 to detect a deadlock or not. Rule 2 is in a resource allocation graph where all the resources are not single instant, but though a cycle is being formed, the system may be in a deadlock state. Okay, if a cycle is being formed, then the system may be in a deadlock state. So we use banker algorithm to confirm whether whether the system is in deadlock state or not. And if no cycle is being formed, then the system is not in a deadlock state. Presence of cycle is necessary, but not a sufficient condition for the occurrence of a deadlock. There may be a cycle formation is there in case of multiple instance. It is not that the cycle formation will make a deadlock situation, because every resources may have more than one instances. So cycle formation never ensure there may be a deadlock situation occurs. Okay, let's see a problem based upon the resource allocation graph. Consider the resource allocation graph in the given figure. Find if the system is in deadlock state, otherwise find a safe sequence. Okay, so let us let us consider the two rule 1 and rule 2, and check whether the system will have a chances of occurring a deadlock or not. Okay, now let us check. See, the process P1 and P2 are two processes, and R1 and R2 are resources. Okay, and P1 already P1 is assigned of resource R1, and P1 is requesting for resource R2, but R2 instance will be given to P2, but P2 is in need of R1. See, a resource with one instant and it forms a cycle. R1 is assigned to P1, but P1 is in need of R2. R2 is assigned to P2, but P2 is in need of R1. So the cycle formation is also there, and no process will execute since it is requesting for some other resources. So this system occurs a deadlock. Okay, so the method 1, the given resource allocation graph is a single instance with a cycle contained in it. So as we saw, we have single instance of a resource and there is a cycle formation. See, P1 is requesting R2, R2 is held by P2, P2 is requesting for R1, but R1 is held by P1. Okay, thus the system is definitely in a deadlock state. Okay, we conclude the system is in deadlock state. Method 2, that is rule 2. Using the given resource allocation graph, we have process 1 has R1 resource and it is requesting for R2. Process 2 have already R2 resource, but it is in need of R1. So availability is 0 and 0. So sure there will be a deadlock occurred. Okay. So now there are no instance available currently, and both the process requires the resources to execute. Therefore, none of the process can be executed, and both keeps waiting indefinitely. Then the system is in a deadlock state. Okay. So consider let us see a second problem. Consider the resource allocation graph in the figure. Find the system is in a deadlock state. Otherwise, find a safe sequence. If there is no deadlock state, we need to find out the system is in a safe sequence by using Banker's algorithm concept. Okay. So just check. We have how many number of process in this resource allocation graph? Process P1 and P2, P3, and P1 is requesting for one of the instance of R2, and one of the instance of R2 is assigned to P3, and R2 instance is assigned to P2, and P2 isn't requesting for resource R1. Let us see whether there is a chances of occurring deadlock or not. If there is no deadlock, we need to find out the safe sequence. Okay, the given resource allocation graph is multiple instance with a cycle contained it. So we have, it is not single instant resources, we have a multiple instances of R2, and there is a cycle formation is also there. Okay. So the system may or may not be in a deadlock state. It may or it may not be in a deadlock state. Using this given resource allocation graph, we have process 1, process 2, process 3. See, check. We need to form a current allocation table, and in this allocation table we have R1 and R2 are the resources, and what are the currently resources allocated to process P1. Resource R1 is allocated. From this diagram you can form this table. See, for the process P1, R1 is allocated. For process P2, one of the instance of R2 is allocated and R2 instance is allocated to P3. So that is given in the current allocation table. Okay, resource R1 is allocated to process P1. R2 resources, one of the instances allocated to process P2 and other instance is allocated to process P3. Okay, now the additional requirement of these three processes are, the process P1 is in need of R2, process P2 is in need of R1, and process P3 is in need of no resources. Okay, so now we need to calculate the availability. Okay, what is the availability of R1 and R2? It is 0 because already it has been allocated for all the process. So you cannot further allocate resources to the process P1, P2 and P3. So since process P3 does not need any resources, so it executes, and after execution process P3 may release its resources. Okay, see, let us see the resource allocation diagram. See, process P3 is not requesting for any other resources, but it is using R2, one of the instance of R2. So let other process wait till the completion of P3. Once the completion of P3 is over, it will release the instance of R2. So now one of the instance of R2 is available. Okay, so this instance may be given to P1. Am I right? See, it completes its execution. Which one? P3 may complete its execution. So what is the availability now? P3 is already 0, 1. Now after using it, we will return the resources. So the current availability of resources are 1 and 1. So with the instance available currently, the requirement of the process P2 can be satisfied. So process P2 is allocated the requested resources. Okay, so because of process P3, you can even allocate resources to process P2, and after using the resources by process P2, all the resources can be released, and now the current availability is 1 1 plus 0 1 is 1 2. So with the help of 1 and 2, you can even allocate to process P1. So the system is in safe state. There is no chances of occurring deadlock, and the sequence of process execution may vary. So what is the safe sequence of execution? First one P3, and later P1, and finally P2. So in which all the process can be executed. So all the processes in the systems are executed, and the order are P3, P1 and P2. So the system is in safe state. Okay, right. Next, let us see the other problem. Consider the resource allocation graph in the figure. Find the system is in a deadlock state, otherwise find a safe sequence. Okay, how many number of process in the resource allocation graph? P1, P0, P1, P2, P3. There are 4 processes, and how many resources with multiple instances? R1 has 2 instances, R2 has 3 instances, and R3 has 2 instances. Okay, now we need to apply the 2 rule and to check or to ensure whether the system occurs deadlock or not, or if it is no deadlock, you need to find out the safe sequence in which order the process may get executed. Okay, now let's see the allocation of resources by the processes. Okay, P0 is holding resource R1, and then also it hold 2 resources, R1 resource and R3 resources, but P1 is also requesting for additional resources of R3. Okay, now P2 is also requesting for the instance of R3, and then R1 resources, one instance is given to P0, other instance is given to P1, but still P1 is in need of R1. And then R2 instances, one is given to P1, the other one is given to P2, the other instance is given to P3, but still P3 is in need of R2. And then R2 instance is also required by P0. Okay, now we need to find out the system is in deadlock state, otherwise find a safe sequence state. Okay, so see, it's somewhat tedious compared to the two problem 1 and problem 2, because there are multiple instances of each resources, as well as we have 4 processes. Let us have a current allocation table. With that table you can easily identify whether a system is in safe state or not. Okay, so the given resource allocation graph is multi-instance with a cycle contained it. So the resource allocation graph is a multiple instance with cycle contained it, where cycle formation is there. So when you see P1 is P1 R1 instances. Okay, P1 is requesting for R1, but R1 is given to P0. P0 is requesting for R3, but R3 is already given to P0, and P0 is requesting for R2. R2 instance is given to P2. P2 is requesting for R3. So there is a cycle formation with multiple instances. Okay, so the system may or may not be in a deadlock state. So let us see, using resource allocation graph, we have a current allocation table. So how many number of process we have in RAG? P0, P1, P2, P3, and three resources, R1, R2, R3. So P0 is allocated R1 and R3. P1 is allocated one instance of R1, one instance of R2, and P2 allocated one instance of R2. P3 is also allocated with one instance of R2. Okay, now what is the additional request, additional need of all these processes? So the additional need of P0 is R2, one of the instance of R2, and one instance from R3. And then additional request by process P2 is one instance from R3, and additional request by P3 are 2. It requires two instance from R2 by P3. Okay, so let us check the availability of R1 and R2 and R3. So the total availability of three resources are, okay, 0 0 1 0 0 1. 0, resource R1 is 0 because all the allocation has been already given, and R2 there is no resources free, but in R3 we have one more resources. See how I can find this availability. Let us go back to this resource allocation graph. See, we have two instance. The two instances given to P1 and P0. So no instance free. That is why that is why given 0 is given here. And similarly for R2, is there any instance free in the resource allocation graph? For R2, see, one instance is given to P1, one instance is given to P2, one instance is given to P3. So there is no instance free in R2. And then for R3, the instance one instance is given to P0. Still one of the instance is not at all allocated. So R3 you have one availability. So 0 0 1. Okay. So now, so with the availability of instance, with the current availability of instances, only the requirement of the process P2 can be satisfied. Okay, so process P2 is allocated the requested resources, and it completes its execution and then free up the instances of the resources held by it. Already allocated for the process P1 is, P2 is, what is the already allocated for process P2? Allocated is 0 1 0. So already allocated is 0 1 0. Now the current available is 0 0 1. So with the availability, we are allocating the requested resources to P2, and after using allocated resources, finally you may get 0 1 1. Okay, 0 plus 0, 0 plus 1 1, 1 plus 0 1. Okay, so let's check with the availability whether we can able to satisfy other process request. Okay, so with the instance available, only the requirement of process P1 can be satisfied. So we finish P2. Now we are looking for the P1 need, and with the availability, we can able to satisfy P1 process request. So process P1 is allocated the requested resources. It completes its execution, then free up the instance of the resources held by it. So what is the already allocated? Allocated of process P1 112, and the currently available is 110. After making use of the process P1 released it, and after summing up you can get the current availability 222. Okay, so the current availability of the system is 222. The requirement of the process P3 can be satisfied. So the process P3 is allocated the requested resources and completes execution, free up the instances resources held by it. And now finally the availability is 220 plus 010, and you will get 232 as an availability, final availability. So with this allocation process, with this allocation order, you may safely allocated the resources to the process without any deadlock situation occurs in the system. Okay, so what is the safe sequence of the execution of a process here? P0, P1 and P3. Okay, so now we can conclude now the system is in safe state. Okay, so the deadlock with the part 1, part 2 and the continuity of part 3 is over. So now we are moving into the next topic. Yeah, so now we are going to see the other topics which is in operating system subject, process, threads and inter-process communication. Okay, let us see what are the topics we are going to discuss under this process concept. In the process concept, we are going to see process scheduling, operation on process, cooperating process, and second topic is threads.